Okay, I'm going to make a series of videos about this set theory, and this comes from a text by Averbach and Coleman. And set theory is very easy, but it's very useful for probability, so it's good to go over it. So first of all, they say a set is a collection of objects. So sometimes, I think that that's just a kind of useless definition because a set and a collection basically mean the same thing, so you're not really saying anything new. But the objects are called elements or members of the set. The set of numbers that we all learn first is this. So now they're talking about a set of numbers, but you don't have to just talk about numbers. But anyway, the set of numbers that we all learn first is the set of natural numbers, and those are these numbers here. And they're also called the positive integers, or they're called counting numbers. This set is adequate for keeping account of how many. However, when we need negative numbers, they say we talk about this set here, and this is the set of positive and negative numbers, and we call them the integers. So one way to describe a set is to list the elements of the set between these, what they call braces, or I'll just call them brackets. The set of all U.S. presidents whose last names begin with the letter T. Okay, so a set doesn't have to be just of numbers. So, okay, looks like that. When set notation is used, an element is listed in a set, and it's listed only once. So we can talk about the set of letters in this word, and notice that we only list the O and the E once. And no indication is given of how often the letter appears. So we just list the set of letters in this word like this. We denote sets usually by uppercase letters like A, B, C, and the members of the set with lowercase letters, usually. And with this notation, an arbitrary set with 5 members might be written like that. To indicate that an element A is a member of a set A, we write A is in A. So this is basically a short way of saying that A is in the set A. And it's read A is an element of A, or A belongs to A. To indicate that an element A is not in a member of the set A, we'll write it this way, which is read A is not an element of A, or A does not belong to A. So suppose we have this set here. We can say 1 is in there. We can say 2 is in there. And we can say 3 is in there, but 4 is not. Okay? At times it's inconvenient or impossible to list the elements of a set. In such cases, the set can often be described by specifying a property that the elements of the set have in common. A convenient way of doing this is to use what is sometimes called set builder notation. So here's an example. This says, the way this is read, is the set of all x, and then this vertical line is read such that x is a positive integer less than 10. So positive integer, so it has to be positive, and it's an integer, not a fraction, less than 10. So we can express it that way, or we could use, do they do it the other way? No, but you can imagine what it will look like. It'll be A equals bracket, then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's another way to express this set. But this is sometimes a convenient way. Okay, here, the set of all IBM stockholders can be written in set builder notation as the set of all x such that x is an IBM stockholder. So this is like a property that x will have. Okay, the next question is, what do we mean by saying that two sets are equal? So we need to define what we mean by sets are equal. And we're going to say that two sets are equal if they have the same elements. And in other words, it doesn't matter which order you write the elements in. So let's see an example of that. So here's a set A. And let's look at that again. A is 1, 2, 3, 4. And B is the set of all x's such that x is a positive integer and x squared is less than 25. So what elements are in this set B? So 1 squared is less than 25, 2 squared is less than 25, 3 squared is less than 25, and 4 squared is less than 25. And those are the only elements. So B is 1, 2, 3, 4 also. So we'll say that A and B are the same. Okay, again, it doesn't matter which order you write them in. Here's an example of that. These sets A and B have the same elements, but they're written in a different order, but that doesn't matter. We still say that A and B are the same. Okay, let's look at this set. What is that? The set of all x such that x is an integer and x squared equals -1. But there's no integer that you can square that gives you -1. So this set has no members, and in such a case we call that the empty set or the null set. Okay? And we use this symbol to indicate the empty set or the null set. So this set has no members, so it's the empty set. Note that this and this we don't use these symbols. Okay? Because the first one contains the element 0 and the second one contains the set this. Okay? Consider the sets this set and this set. Notice that every element of A is also an element of B, right? Check it. A is in B, O is in B, and U is in B. In that case, we say that A is a subset of B. A is a subset of B because every element in A is in B. And we write that like this. A is a subset of B. They say, note that, well, it's not so clear, but the empty set is a subset of every set. Okay, the reason for that is that in order to show that one set is not a subset of another set, so if I wanted to prove that A was not a subset of B, of course it is this time, but if I wanted to show that some set A was not a subset of B, what would I have to do? I'd have to find an element in the set A which was not in the set B. Okay? But if I try to do that for the empty set, I can't do it. I can't find an element of the empty set which is not in, say, B. So therefore the empty set we will say that the empty set is a subset of B, and similarly for any set B, the empty set will always be a subset of, in other words, of every set. And also, okay, look at this set B. We can ask what are all the subsets of B, and we list them here. So this is clearly a subset of B. This is clearly a subset of B. This is clearly a subset of B. This is a subset of B. So is this. So is this. And also, technically speaking, this is a subset of B, because every element in here is in B. So actually B is a subset of itself. In fact, every set is a subset of itself. And again, this one is also a subset of B. So these are all possible subsets of B. How many are there? 1, 2, 3, 4, 5, 6, 7, 8. Okay. Let's take this example. Let A be the set of all x such that x is a positive even integer. And let B be the set of all x's such that x is an integer. So clearly A is a subset of B. That is, if something is a positive even integer, and it's an integer, if something is a positive even integer, then clearly it's an integer. So every element in A is also in B. Here's another example. If S is the set of all stocks listed in the New York Stock Exchange on this date, and T is the set of all stocks on the New York Stock Exchange that traded over 100 shares on the same date, then clearly T is a subset of S, right? Okay. And here they mention that every set is a subset of itself. And then also, what does this symbol mean? So here we have a picture A and B, and clearly the meaning, I guess, is that A is not a subset of B. And similarly, B is not a subset of A. Okay, if you want to read this, go ahead and read it. Let A be the set of points inside the larger circle in figure 2, and let B be the set of points in the smaller circle. Then this picture means that B is a subset of A. A is not a subset of B. Okay. Okay, let's stop here. You can check these exercises if you like. And I'll continue here.